Welcome to the first lecture of this class. You may be used to having a first lecture devoted to general comments and motivating examples. This one will be different. We will dive into the heart of the subject right away. In fact, today we will accomplish a lot. By the end of this lecture, you will know about all of the elements of a probabilistic model. A probabilistic model is a quantitative description of a situation, a phenomenon, or an experiment whose outcome is uncertain. Putting together such a model involves two key steps. First, we need to describe the possible outcomes of the experiment. This is done by specifying a so-called sample space. And then we specify a probability law which assigns probabilities to outcomes or to collections of outcomes. The probability law tells us, for example, whether one outcome is much more likely than some other outcome. Probabilities have to satisfy certain basic properties in order to be meaningful. These are the axioms of probability theory. For example, probabilities cannot be negative. Interestingly, there will be very few axioms, but they are powerful, and we will see that they have lots of consequences. We will see that they imply many other properties that were not part of the axioms. We will then go through a couple of very simple examples involving models with either discrete or continuous outcomes. As you will be seeing many times in this class, discrete models are conceptually much easier. Continuous models involve some more sophisticated concepts, and we will point out some of the subtle issues that arise. And finally, we will talk a little bit about the big picture, about the role of probability theory and its relation with the real world. Putting together a probabilistic model, that is, a model of a random phenomenon or a random experiment, involves two steps. First step, we describe the possible outcomes of the phenomenon or experiment of interest. Second step, we describe our beliefs about the likelihood of the different possible outcomes by specifying a probability law. Here we start by just talking about the first step, namely the description of the possible outcomes of the experiment. So we carry out an experiment. For example, we flip a coin, or maybe we flip 5 coins simultaneously, or maybe we roll a die. Whatever that experiment is, it has a number of possible outcomes, and we start by making a list of the possible outcomes. Or a better word, instead of the word list, is to use the word set, which has a more formal mathematical meaning. So we create a set that we usually denote by capital omega. That set is called the sample space and is the set of all possible outcomes of our experiment. The elements of that set should have certain properties. Namely, the elements should be mutually exclusive and collectively exhaustive. What does that mean? Mutually exclusive means that if at the end of the experiment I tell you that this outcome happened, then it should not be possible that this outcome also happened. At the end of the experiment, there can only be one of the outcomes that has happened. Being collectively exhaustive means something else, that together all these elements of the set exhaust all the possibilities. So no matter what, at the end you will be able to point to one of the outcomes and say that's the one that occurred. To summarize, this set should be such that at the end of the experiment you should be always able to point to one and exactly one of the possible outcomes and say that this is the outcome that occurred. Physically different outcomes should be distinguished in the sample space and correspond to distinct points. But when we say physically different outcomes, what do we mean? We really mean different in all relevant aspects, but perhaps not different in irrelevant aspects. Let's make more precise what I mean by that by looking at a very simple and maybe silly example, which is the following. Suppose that you flip a coin and you see whether it resulted in heads or tails. So you have a perfectly legitimate sample space for this experiment, which consists of just 2 points, heads and tails. Together, these two outcomes exhaust all possibilities, and the two outcomes are mutually exclusive. So this is a very legitimate sample space for this experiment. Now suppose that while you were flipping the coin, you also looked outside the window to check the weather. And then you could say that my sample space is really heads and it's raining. Another possible outcome is heads and no rain. Another possible outcome is tails and it's raining. And finally, another possible outcome is tails and no rain. This set, consisting of 4 elements, is also a perfectly legitimate sample space for the experiment of flipping a coin. The elements of this sample space are mutually exclusive and collectively exhausted. Exactly one of these outcomes is going to be true or will have materialized at the end of the experiment. So which sample space is the correct one? This sample space, the second one, involves some irrelevant details. So the preferred sample space for describing the flipping of a coin, the preferred sample space is the simpler one, the first one, which is sort of at the right granularity given what we're interested in. But ultimately, the question of which one is the right sample space depends on what kind of questions you want to answer. For example, if you have a theory that the weather affects the behavior of coins, then in order to play with that theory or maybe check it out and so on, then in such a case you might want to work with a second sample space. This is a common feature in all of science. Whenever you put together a model, you need to decide how detailed you want your model to be, and the right level of detail is the one that captures those aspects that are relevant and of interest to you. Let us now look at some examples of sample spaces. Sample spaces are sets, and the set can be discrete, finite, infinite, continuous, and so on. Let us start with a simpler case in which we have a sample space that is discrete and finite. The particular experiment we will be looking at is the following. We take a very special die, a tetrahedral die, so it's a die that has 4 faces, numbered from 1 up to 4. We roll it once, and then we roll it twice. We're not dealing here with 2 probabilistic experiments, we're dealing with a single probabilistic experiment that involves 2 rolls of the die within that experiment. What is the sample space of that experiment? Well, one possible representation is the following. We take note of the result of the first roll, and then we take note of the result of the second roll, and this gives us a pair of numbers. Each one of the possible pairs of numbers corresponds to one of the little squares in this diagram. For example, if the first roll is 1 and the second is also 1, then this particular outcome has occurred. If the first roll is a 2 and the second is a 3, then this particular outcome occurs. If the first roll is a 3 and then the next one is a 2, then this particular outcome occurs. Notice that these two outcomes are pretty closely related. In both cases, we observe a 2 and we observe a 3, but we distinguish those two outcomes because in those two outcomes, the 2 and the 3 happen in different order. And the order in which they appear may be a detail which is of interest to us, and so we make this distinction in the sample space. So we keep the 3-2 and the 2-3 as separate outcomes. Now, this is a case of a model in which the probabilistic experiment can be described in phases or stages. We could think about rolling the die once and then going ahead with the second roll. So we have two stages. A very useful way of describing the sample space of experiments. Whenever we have an experiment with several stages, either real stages or imagined stages, so a very useful way of describing it is by providing a sequential description in terms of a tree. So a diagram of this kind, we call it a tree. You can think of this as the root of the tree from which you start, and the end points of the tree, we usually call them the leaves. So the experiment starts, we carry out the first phase, which in this case is the first roll, and we see what happens. So maybe we get a 2 in the first roll. And then we take note of what happened in the second roll, and maybe the result was a 3. So we follow this branch here, and we end up at this particular leaf, which is the leaf associated with the outcome 2, 3. Notice that in this tree, we once more have a distinction. The outcome 2 followed by a 3 is different from the outcome 3 followed by a 2, which would correspond to this particular place in the diagram. In both cases, we have 16 possible outcomes. 4 times 4 makes 16, and similarly, if you count here, the number of leaves is equal to 16. The previous example involved a sample space that was discrete and finite. There were only 16 possible outcomes. But sample spaces can also be infinite, and they could also be continuous sets. Here's an example of an experiment that involves a continuous sample space. So we have a rectangular target, which is the unit square, and you throw a dart on that target. And suppose that you are so skilled that no matter what, when you throw the dart, it always falls inside the target. Once the dart hits the target, you record the coordinates x and y of the particular point that resulted from your dart throw. And we record x and y with infinite precision, so x and y are real numbers. So in this experiment, the sample space is just the set of xy pairs that lie between 0 and 1. We have so far discussed the first step involved in the construction of a probabilistic model, namely the construction of a sample space, which is a description of the possible outcomes of a probabilistic experiment. We now come to the second and much more interesting part. We need to specify which outcomes are more likely to occur and which ones are less likely to occur, and so on. And we will do that by assigning probabilities to the different outcomes. However, as we try to do this assignment, we run into some kind of difficulty, which is the following. Remember the previous experiment involving a continuous sample space which was the unit square, and in which we throw a dart at random and record the point that occurred? In this experiment, what do you think is the probability of a particular point? Let's say, what is the probability that my dart hits exactly the center of this square? Well, this probability would be essentially 0. Hitting the center exactly with infinite precision should be 0. And so it's natural that in such a continuous model, any individual point should have a 0 probability. For this reason, instead of assigning probabilities to individual points, we will instead assign probabilities to whole sets, that is, to subsets of the sample space. So here we have our sample space, which is some abstract set omega. Here's a subset of the sample space, call it capital A. We're going to assign a probability to that subset A, which we're going to denote with this notation, which we read as the probability of set A.
So probabilities will be assigned to subsets, and this will not cause us difficulties in the continuous case, because even though individual points would have zero probability, if you ask me what are the odds that my dart falls in the upper half, let's say, of this diagram, then that should be a reasonable positive number. So even though individual outcomes may have zero probabilities, sets of outcomes in general would be expected to have positive probabilities. So coming back, we're going to assign probabilities to the various subsets of the sample space. And here comes a piece of terminology that a subset of the sample space is called an event. Why is it called an event? Because once we carry out the experiment and we observe the outcome of the experiment, either this outcome is inside the set A, and in that case we say that event A has occurred, or the outcome falls outside the set A, in which case we say that event A did not occur. Now we want to move on and describe certain rules, the rules of the game in probabilistic models, which are basically the rules that these probabilities should satisfy. They shouldn't be completely arbitrary. First, by convention, probabilities are always given in a range between 0 and 1. Intuitively, 0 probability means that we believe that something practically cannot happen, and probability of 1 means that we're practically certain that, that an event of interest is going to happen. So we want to specify rules of this kind for probabilities. These rules that any probabilistic model should satisfy are called the axioms of probability theory. And our first axiom is a non-negativity axiom. Namely, probabilities will always be non-negative numbers. It's a reasonable rule. The second rule is that if the subset that we're looking at is actually not a subset, but is the entire sample space omega, the probability of it should always be equal to 1. What does that mean? We know that the outcome is going to be an element of the sample space. This is the definition of the sample space. So we have absolute certainty that our outcome is going to be in omega, or in different language, we have absolute certainty that event omega is going to occur, and we capture this certainty by saying that the probability of event omega is equal to 1. These two axioms are pretty simple and very intuitive. The more interesting axiom is the next one that says something a little more complicated. Before we discuss that particular axiom, a quick reminder about set theoretic notation. If we have two sets, let's say a set A and another set B, we use the notation, we use this particular notation, which we read as A intersection B, to refer to the collection of elements that belong to both A and B. So in this picture, the intersection of A and B is this shaded set. We use this notation, which we read as A union B, to refer to the set of elements that belong to A, or to B, or to both. So in terms of this picture, the union of the two sets would be this blue set. After this reminder about set theoretic notation, now let us look at the form of the third axiom. What does it say? If we have two sets, two events, two subsets of the sample space, which are disjoint. So here's our sample space, and here are the two sets that are disjoint. In mathematical terms, two sets being disjoint means that their intersection has no elements, so their intersection is the empty set, and we use this symbol here to denote the empty set. So if the intersection of two sets is empty, then the probability that the outcome of the experiment falls in the union of A and B, That is, the probability that the outcome is here or there is equal to the sum of the probabilities of these two sets. This is called the additivity axiom. So it says that we can add probabilities of different sets when those two sets are disjoint. In some sense, we can think of probability as being 1 pound of some substance which is spread over our sample space, and the probability of A is how much of that substance is sitting on top of a set A. So what this axiom is saying is that the total amount of that substance sitting on top of A and B is how much is sitting on top of A plus how much is sitting on top of B. And that is the case whenever the sets A and B are disjoint from each other. The additivity axiom needs to be refined a bit. We will talk about that a little later. Other than this refinement, these three axioms are the only requirements in order to have a legitimate probability model. At this point you may ask, shouldn't there be more requirements? Shouldn't we, for example, say that probabilities cannot be greater than 1? Yes and no. We do not want probabilities to be larger than 1, but we do not need to say it. As we will see in the next segment, such a requirement follows from what we have already said, and the same is true for several other natural properties of probabilities. The probability axioms are the basic rules of probability theory, and they are surprisingly few, but they imply many interesting properties that we will now explore. First, we will see that what you might think of as missing axioms are actually implied by the axioms already in place. For example, we have an axiom that probabilities are non-negative. We will show that probabilities are also less than or equal to 1. We have another axiom that says that the probability of the entire sample space is 1. We will show a counterpart that the probability of the empty set is equal to 0. This makes perfect sense. The empty set has no elements, so it is impossible. There is 0 probability that the outcome of the experiment would lie in the empty set. We also have another intuitive property. The probability that an event happens plus the probability that the event does not happen exhaust all possibilities, and these two probabilities together should add to 1. For instance, if the probability of heads is 0.6, then the probability of tails should be 0.4. Finally, we can generalize the additivity axiom, which was originally given for the case of two disjoint events, to the case where we're dealing with the union of several disjoint events. By disjoint, here we mean that the intersection of any two of these events is the empty set. We will prove this for the case of 3 events, and then the argument generalizes for the case where we're taking the union of k disjoint events, where k is any finite number. So the intuition of this result is the same as for the case of 2 events, but we will derive it formally, and we will also use it to come up with a way of calculating the probability of a finite set by simply adding the probabilities of its individual elements. All of these statements that we just presented are intuitive, and you do not really need to be convinced about their validity. Nevertheless, it is instructive to see how these statements follow from the axioms that we have put in place. So we will now present the arguments based only on the 3 axioms that we have available. And in order to be able to refer to these axioms, let us give them some names, call them axioms A, B, and C. We start as follows. Let us look at a sample space and a subset of that sample space, call it A, and consider the complement of that subset. The complement is the set of all elements that do not belong to the set A. So a set together with its complement make up everything, which is the entire sample space. On the other hand, if an element belongs to a set A, it does not belong to its complement, so the intersection of a set with its complement is the empty set. Now we argue as follows. We have that the probability of the entire sample space is equal to 1. This is true by our second axiom. Now the sample space, as we just discussed, can be written as the union of an event and the complement of that event. This is just a set theoretic relation. And next, since a set and its complement are disjoint, this means that we can apply the additivity axiom and write this probability as the sum of the probability of event A with the probability of the complement of A. This is one of the relations that we had claimed and which we have now established. Based on this relation, we can also write that the probability of an event A is equal to 1 minus the probability of the complement of that event. And because by the non-negativity axiom this quantity here is non-negative, 1 minus something non-negative is less than or equal to 1. We're using here the non-negativity axiom, and we have established another property, namely that probabilities are always less than or equal to 1. Finally, let us note that 1 is the probability always of a set plus the probability of a complement of that set. And let us use this property for the case where the set of interest is the entire sample space. Now, the probability of the entire sample space is itself equal to 1. And what is the complement of the entire sample space? The complement of the entire sample space consists of all elements that do not belong to the sample space. But since the sample space is supposed to contain all possible elements, its complement is just the empty set. And from this relation, we get the implication that the probability of the empty set is equal to 0. This establishes yet one more of the properties that we had just claimed a little earlier. We finally come to the proof of the generalization of our additivity axiom from the case of 2 disjoint events to the case of 3 disjoint events. So we have our sample space, and within that sample space we have 3 events, 3 subsets, and these subsets are disjoint in the sense that any 2 of those subsets have no elements in common. And we're interested in the probability of the union of A, B, and C. How do we make progress? We have an additivity axiom in our hands which applies to the case of the union of 2 disjoint sets. Here we have 3 of them. But we can do the following trick. We can think of the union of A, B, and C as consisting of the union of this blue set with that green set. Formally, what we're doing is that we're expressing the union of these 3 sets as follows. We form one set by taking the union of A with B, and we have the other set C, and the overall union can be thought of as the union of these 2 sets. Now, since the 3 sets are disjoint, this implies that the blue set is disjoint from the green set, and so we can use the additivity axiom here to write this probability as the probability of A union B plus the probability of C. And now we can use the additivity axiom once more, since the sets A and B are disjoint, to write the first term as probability of A plus probability of B. We carry over the last term, and we have the relation that we wanted to prove. This is the proof for the case of 3 events. You should be able to follow this line of proof to write an argument for the case of 4 events and so on, and you might want to continue by induction, and eventually you should be able to prove that if the sets A1 up to AK are disjoint, then the probability of the union of those sets is going to be equal to the sum of their individual probabilities. So this is the generalization to the case where we're dealing with the union of finitely many disjoint events. A very useful application of this comes in the case where we want to calculate the probability of a finite set. So here we have a sample space, and within that sample space we have some particular elements, S1, S2 up to Sk, k of them, and these elements together form a finite set. What can we say about the probability of this finite set? The idea is to take this finite set that consists of k elements and think of it as the union of several little sets that contain one element each. So set theoretically, what we're doing is that we're taking this set with k elements and we write it as the union of a set that contains just S1, a set that contains just the second element S2, and so on, up to the kth element. We're assuming, of course, that these elements are all different from each other. So in that case, these sets, these single element sets, are all disjoint. So using the additivity property for a union of k disjoint sets, we can write this as the sum of the probabilities of the different single element sets. At this point, it is usual to start abusing, or rather simplifying, notation a little bit. Probabilities are assigned to sets, so here we're talking about the probability of a set that contains a single element, but intuitively we can also talk as just the probability of that particular element and use this simpler notation. So when using this simpler notation, we will be talking about the probabilities of individual elements, although in terms of formal mathematics, what we really mean is the probability of this event that's comprised only of a particular element, S1, and so on. We will now continue and derive some additional properties of probability laws, which are again consequences of the axioms that we have introduced. The first property is the following. If we have two sets and one set is smaller than the other, so we have a picture as follows. We have our sample space and we have a certain set A, and then we have a certain set B which is even bigger, so the set B is the bigger blue set. So if B is a set which is larger than A, then naturally the probability that the outcome falls inside B should be at least as big as the probability that the outcome falls inside A. How do we prove this formally? The set B can be expressed as a union of two pieces. One piece is the set A itself. The second piece is whatever elements of B there are that do not belong in A. What are these elements? They are elements that belong to B and they do not belong to A, which means that they belong to the complement of A. So we have expressed the set B as the union of two pieces. Now this piece is A, this piece here is outside A. So these two pieces are disjoint, and so we can apply the additivity axiom and write that the probability of B is equal to the probability of A plus the probability of the other set. And since probabilities are non-negative, this expression here is at least as large as the probability of A, and this concludes the proof of the property that we wanted to show. Indeed, the probability of A is less than or equal to the probability of B. The next property we will show is the following. It allows us to write the probability of the union of two sets for the case now where the two sets are not necessarily disjoint. So the picture is as follows. We have our two sets, A and B. These sets are not necessarily disjoint. And we want to say something about the probability of the union of A and B. Okay, now the union of A and B consists of three pieces. One piece is this one here, and that piece consists of those elements of A that do not belong to B, so they belong to B complement. This set has a certain probability, let's call it little a, and indicate it on this diagram. So A is the probability of this piece. Another piece is this one here, which is the intersection of A and B. It has a certain probability that we denote by little b. This is the probability of A intersection B. And finally, there's another piece, which is out here. And that piece has a certain probability C. It's the probability of that set. And what is that set? That set is the following. It's that part of B that consists of elements that do not belong in A. So it's B intersection with the complement of A. Now let's express the two sides of this equality here in terms of little a, little b, and little c, and see whether we get the same thing. So the probability of A union B. A union B consists of these three pieces that have probabilities A, little b, and little c, respectively. And by the additivity axiom, the probability of the union of A and B is the sum of the probabilities of these three pieces. Let's look now at the right-hand side of that equation and see whether we get the same thing. The probability of A plus the probability of B minus the probability of A intersection B is equal to the following. A consists of two pieces that have probabilities little a and little b. The set B consists of two pieces that have probabilities little b and little c. And then we subtract the probability of the intersection, which is b. And we notice that we can cancel here one b with another b, and what we are left with is a plus b plus c. So this checks, and indeed we have this equality here. We have verified that it is true. One particular consequence of the equality that we derived is the following. Since this term here is always non-negative, this means that the probability of A union B is always less than or equal to the probability of A plus the probability of B. This inequality here is quite useful whenever we want to argue that a certain probability is smaller than something, and it has a name. It's called the union bound. We finally consider one last consequence of our axioms, and namely we're going to derive an expression, a way of calculating the probability of a union of three sets, not necessarily disjoint. So we have our sample space, and within the sample space there are three sets. Set A, set B, and set C. We're going to use a set theoretic relation. We're going to express the union of these three sets as the union of three disjoint pieces. What are these disjoint pieces? One piece is the set A itself. The second piece is going to be that part of B which is outside A. So this is the intersection of B with the complement of A. The third piece is going to be whatever is left in order to form the union of the three sets. What is left is that part of C that does not belong to A and that does not belong into B. So that part is C intersection with A complement and B complement. Now, this set here, of course, is the same as that set, because intersection of two sets is the same no matter in which order we take the two sets. And similarly, the set that we have here is the same one that appears in that expression. Now, we notice that these three pieces, the red, the blue, and the green, are disjoint from each other. So, by the additivity axiom, the probability of this union here is going to be the sum of the probabilities of the three pieces, and that's exactly the expression that we have up here. Let us now move from the abstract to the concrete. Recall the example that we discussed earlier, where we have two rolls of a tetrahedral die, so there are 16 possible outcomes illustrated in this diagram. To continue, now we need to specify a probability law, some kind of probability assignment. To keep things simple, we're going to make the assumption that the 16 possible outcomes are all equally likely and each outcome has a probability of 1 over 16. Given this assumption, we will now proceed to calculate certain probabilities. Let us look first at the probability that x, which stands for the result of the first roll, is equal to 1. The way to calculate this probability is to identify what exactly that event is in our picture of the sample space and then calculate. The event that x is equal to 1 can happen in 4 different ways that correspond to these 4 particular outcomes. Each one of these outcomes has a probability of 1 over 16. The probability of this event is the sum of the probabilities of the outcomes that it contains, so it is 4 times 1 over 16 equal to 1/4. Let now z stand for the smaller of the two numbers that came up in our two rolls. So, for example, if x is 2 and y is equal to 3, then z is equal to 2, which is the smaller of the two. Let us try to calculate the probability that the smaller of the two outcomes is equal to 4. Now, for the smaller of the two outcomes to be equal to 4, we must have that both x and y are equal to 4. So this outcome here is the only way that this particular event can happen. So since there's only one outcome that makes the event happen, the probability of this event is the probability of that outcome and is equal to 1 over 16. For another example, let's calculate the probability that the minimum is equal to 2. What does it mean that the minimum is equal to 2? It means that one of the dice resulted in a 2 and the other die resulted in a number that's 2 or larger. So we could have both equal to 2. We could have x equal to 2 but y larger, or we could have y equal to 2 and x something larger. This green event, this green set, is the set of all outcomes for which the minimum of the two rolls is equal to 2. There's a total of 5 such outcomes. Each one of them has probability 1 over 16, and we have discussed that for finite sets, the probability of a finite set is the sum of the probabilities of the elements of that set. So we have 5 elements here, each one with probability 1 over 16, and this is the answer to this problem. This particular example that we saw here is a special case of what is called a discrete uniform law. In a discrete uniform law, we have a sample space which is finite and it has n elements, and we assume that these n elements are equally likely. Now, since the probability of omega, the probability of the entire sample space, is equal to 1, this means that each one of these elements must have probability 1 over n. That's the only way that the sum of the probabilities of the different outcomes would be equal to 1 as required by the normalization axiom. Consider now some subset of the sample space, an event A, that has exactly k elements. What is the probability of the set A? It's the sum of the probabilities of its elements. There are k elements, and each one of them has a probability of 1 over n, and this way we can find the probability of the set A. So when we have a discrete uniform probability law, we can calculate probabilities by simply counting the number of elements of omega, which is n, finding the number n, and counting the number of elements of the set A. That's the reason why counting will turn out to be an important skill, and there will be a whole lecture devoted to this particular topic. We will now go through a probability calculation for the case where we have a continuous sample space. We revisit our earlier example in which we were throwing a dart into a square target, the square target being the unit square, and we were guaranteed that our dart would fall somewhere inside this set. So our sample space is the unit square itself. We have a description of the sample space, but we do not yet have a probability law. We need to specify one. The choice of a probability law could be arbitrary. It's up to us to choose how to model a certain situation. And to keep things simple, we're going to assume that our probability law is a uniform one, which means that the probability of any particular subset of the sample space is going to be the area of that subset. So if we have some subset lying somewhere here, and we ask what is the probability that we fall into that subset, the probability is exactly the area of that particular subset. Once more, this is an arbitrary choice of a probability law. There's nothing in our assumption so far that would force us to make this particular choice, and we just use it for the purposes of this example. So now let us calculate some probabilities. Let us look at this event. This is the event that the sum of the two numbers that we get in our experiment is less than or equal to 1/2. It is always useful to work in terms of a picture and to depict that event in a picture of the sample space. So in terms of that sample space, the points that make this event to be true are just a triangle that lies below the line where this is the line that x plus y equals to 1/2. Anything below that line, these are the outcomes that make this event happen. So we're trying to find the probability of this red event. We have assumed that probability is equal to area. Therefore, the probability we're trying to calculate is the area of a triangle. And the area of a triangle is 1/2 times the base of the triangle, which is 1/2 in our case, times the height of the triangle, which is again 1/2 in our case, and the end result is 1/8. Let us now calculate another probability. Now this is an event that consists of only a single element. We take the point 0.5, 0.3, which sits somewhere here. The event of interest is a set, but that set consists of a single point. So we're asking for the probability that our dart falls exactly on top of that point. What is it? Well, it is the area of a set that consists of a single point. What is the area of a single point? It is 0. And similarly, for any other single point inside that sample space that we might have considered, the answer is going to be 0. Let us now abstract from this example, as well as the previous one, and note the following. Probability calculations involve a sequence of 4 steps, starting with a word description of a problem, of a probabilistic experiment. We first write down the sample space. Then we specify a probability law. Let me emphasize again here that this step has some arbitrariness in it. You can choose any probability law you like, although for your results to be useful, it would be good if your probability law captures the real-world phenomenon you're trying to model. Typically, you're interested in calculating the probability of some event. That event may be described in some loose manner, so you need to describe it mathematically. And if possible, it's always good to describe it in terms of a picture. Pictures are immensely useful when going through this process. And finally, the last step is to go ahead and calculate the probability of the event of interest. Now, a probability law in principle specifies the probability of every event, and there is nothing else to do. But quite often the probability law will be given in some implicit manner, for example by specifying the probabilities of only some of the events. In that case, you may have to do some additional work to find the probability of the particular event that you care about. This last step sometimes will be easy. Sometimes it may be complicated, but in either case, by following this 4-step procedure and by being systematic, you will always be able to come up with a single correct answer. We have seen so far an example of a probability law on a discrete and finite sample space, as well as an example with an infinite and continuous sample space. Let us now look at an example involving a discrete but infinite sample space. We carry out an experiment whose outcome is an arbitrary positive integer. As an example of such an experiment, suppose that we keep tossing a coin and the outcome is the number of tosses until we observe heads for the first time. The first heads might appear in the first toss, or the second, or the third, and so on. So in this example, any positive integer is possible, and so our sample space is infinite. Let us now specify a probability law. A probability law should determine the probability of every event, of every subset of the sample space, that is, the probability of every set of positive integers. But instead, I will just tell you the probability of events that contain a single element. I'm going to tell you that there is probability 1 over 2 to the n that the outcome is equal to n. Is this good enough? Is this information enough to determine the probability of any subset? Before we look into that question, let us first do a quick sanity check to see whether these numbers that were given look like legitimate probabilities. Do they add to 1? Let's do a quick check. So the sum over all the possible values of n of the probabilities that were given, which is an infinite sum from n starting from 1 all the way up to infinity of 1 over 2 to the n, is equal to the following. First, we take out a factor of 1/2 from all these terms, which reduces the exponent from n to minus 1, or this is the same as running the sum from n equal 0 to infinity of 1/2 and to the n. And now we have a usual infinite geometric series, and we have a formula for this. The geometric series has a value of 1 minus the number whose power we're taking, which is 1/2. And after we do the arithmetic, this turns out to be equal to 1. So indeed, it appears that we have the basic elements of what it would take to have a legitimate probability law. But now let us look into how we might calculate the probability of some general event. For example, the probability that the outcome is even. We proceed as follows. The probability that the outcome is even, this is the probability of an infinite set that consists of all the even integers. We can write this set as the union of lots of little sets that contain a single element each. So it's the set containing the number 2, the set containing the number 4, the set containing the number 6, and so on. At this point, we notice that we're talking about the probability of a union of sets, and these sets are disjoint because they contain different elements. So we can use an additivity property and say that this is the probability of obtaining a 2 plus the probability of obtaining a 4 plus the probability of obtaining a 6 and so on. If you're curious about doing this calculation and actually obtaining a numerical answer, you would proceed as follows. You notice that this is 1 over 2 to the second power plus 1 over 2 to the fourth power plus 1 over 2 to the sixth power, and so on. Now you factor out a factor of 1/4, and what you're left is 1 plus 1 over 2 to the second power, which is 1/4, plus 1 over 2 to the fourth power, which is the same as 1/4 to the second power, and so on. And now we have 1/4 times the infinite sum of a geometric series, which gives us 1 minus 1 over 1 minus 1/4. And after you do the algebra, you obtain a numerical answer, which is equal to 1/3. But leaving the details of the calculation aside, the more important question I want to address is the following. Is this calculation correct? We seem to have used an additivity property at this point, but the additivity properties that we have in our hands at this point only talk about disjoint unions of finitely many subsets. Our initial axiom talked about a disjoint union of two subsets, and then later on we established a similar property for a disjoint union of finitely many subsets. But here we're talking about the union of infinitely many subsets. So this step here is not really allowed by what we have in our hands. On the other hand, we would like our theory to allow this kind of calculation. The way out of this dilemma is to introduce an additional axiom that will indeed allow this kind of calculation. The axiom that we introduce is the following. If we have an infinite sequence of disjoint events, as for example in this picture, we have our sample space, we have a first event A1, we have a second event A2, a third event A3, and so we keep continuing and we have an infinite sequence of such events. Then the probability of the union of these events, of these infinitely many events, is the sum of their individual probabilities. The key word here is the word sequence. Namely, these events, these sets that we're dealing with, can be arranged so that we can talk about the first event, A1, the second event, A2, the third one, A3, and so on. To appreciate the issue that arises here and to see why the word sequence is so important, let us consider the following calculation. Our sample space is the unit square, and we consider a model where the probability of a set is its area. as in the examples that we considered earlier. Let us now look at the probability of the overall sample space. Our sample space is the unit square, and the unit square can be thought of as the union of various sets that consist of single points. So it's the union of subsets with one element each, and it's a union taken over all the points in the unit square. Then we think about additivity. We observe that these subsets are disjoint. If we're considering different points, then we get disjoint single element sets. And then an additivity property would tell us that the probability of this union is the sum of the probabilities of the different single element subsets. Now, as we discussed before, single element subsets have zero probability, so we have a sum of lots of zeros, and the sum of zeros should be equal to 0. On the other hand, by the probability axioms, the probability of the entire sample space should be equal to 1, and so we have established that 1 is equal to 0. This looks like a paradox. Is it? The catch is that there is nothing in the axioms we have introduced so far, or the properties we have established, that would justify this step. So this step here is questionable. You might argue that the unit square is the union of disjoint single element sets, which is the case that we have in additivity axioms, but the additivity axiom only applies when we have a sequence of events. And this is not what we have here. This is not a union of a sequence of single element sets. In fact, there is no way that the elements of the unit square can be arranged in a sequence. The unit square is said to be an uncountable set. This is a deep and fundamental mathematical fact. What it essentially says is that there are two kinds of infinite sets: discrete ones, or in formal terminology, countable. These are sets whose elements can be arranged in a sequence, like the integers. And also uncountable sets, such as the unit square or the real line, whose elements cannot be arranged in a sequence. If you're curious, you can find the proof of this important fact in the supplementary materials that we are providing. After all this discussion, you may now have legitimate suspicions about the models we have been looking at. Is area a legitimate probability law? Does it even satisfy countable additivity? This question takes us into deep waters and has to do with a deep subfield of mathematics called measure theory. Fortunately, it turns out that all is well. Area is a legitimate probability law. It does indeed satisfy the countable additivity axiom, as long as we only deal with nice subsets of the unit square. Fortunately, the subsets that arise in whatever we do in this course will be nice. Subsets that are not nice are quite pathological, and we will not encounter them. At this stage, we're not in a position to say anything more that would be meaningful about these issues because they're quite complicated and mathematically deep. We can only say that there are some serious mathematical subtleties, but fortunately they can all be overcome in a rigorous manner. And for the rest of this class, you can just forget about these subtle issues. We end this lecture sequence by stepping back to discuss what probability theory really is and what exactly is the meaning of the word probability. In the most narrow view, probability theory is just a branch of mathematics. We start with some axioms, we consider models that satisfy these axioms, and we establish some consequences, which are the theorems of this theory. You could do all that without ever asking the question of what the word probability really means. Yet, one of the theorems of probability theory that we will see later in this class is that probabilities can be interpreted as frequencies. Very loosely speaking, if I have a fair coin and I toss it infinitely many times, then the fraction of heads that I will observe will be 1/2. In this sense, the probability of an event A can be interpreted as the frequency with which event A will occur in an infinite number of repetitions of the experiment. But is this all there is? If we're dealing with coin tosses, it makes sense to think of probabilities as frequencies. But consider a statement such as, the current president of my country will be re-elected in the next election with probability 0.7. It is hard to think of this number 0.7 as a frequency. It does not make sense to think of infinitely many repetitions of the next election. In cases like this, and in many others, it is better to think of probabilities as just some way of describing our beliefs. And if you're a betting person, probabilities can be thought of as some numerical guidance into what kinds of bets you might be willing to make. But now, if we think of probabilities as beliefs, you can run into the argument that, well, beliefs are subjective. Isn't probability theory supposed to be an objective part of math and science? Is probability theory just an exercise in subjectivity? Well, not quite. There is more into it. Probability, at the minimum, gives us some rules for thinking systematically about uncertain situations. And if it happens that our probability model, our subjective beliefs, have some relation with the real world, then probability theory can be a very useful tool for making predictions and decisions that apply to the real world. Now, whether your predictions and decisions will be any good will depend on whether you have chosen a good model. Have you chosen a model that provides a good enough representation of the real world? How do you make sure that this is the case? There is a whole field, the field of statistics, whose purpose is to complement probability theory by using data to come up with good models. And so we have the following diagram that summarizes the relation between the real world, statistics, and probability. The real world generates data. The field of statistics and inference uses these data to come up with probabilistic models. Once we have a probabilistic model, we use probability theory and the analysis tools that it provides to us, and the results that we get from this analysis lead to predictions and decisions about the real world.